Very good morning. Bonjour à tous. Thank you for taking time to join us for this webinar. This is the second in a series of webinars about DAS and PRODML, and you received a link to see the recording of the first webinar in your invitation. First of all, a few words about the presenters. Kit CHOI is scientific software developer at Enthought. She's been heavily involved in PRODML over the past 2 years and will be leading a fair chunk of this presentation. Laurence OMEROD is the PRODML project manager, consultant to Energistics, has been for a long time involved around all things PRODML, and he will also be contributing to this talk. Just for your information, the webinar will be recorded and available on our website a couple of hours after the end of this event. We'll be entertaining questions and answers at the end of the formal presentation, so feel free to type in any questions you may have for the presenters. There will be a survey at the end of the webinar, and we would be very appreciative if you could take a few minutes to answer a couple of simple questions that help us organize more relevant and informative webinars going forward. Attendees are not given the right to talk, so just that's part of our protocol, basically running these events. So without further ado, Laurence, I'll let you do the introduction to Energistics. Thank you very much. Laurence? Go ahead, Laurence.
Right. Yes, can you hear me now?
I hear you.
Yeah, okay, great. All right, so hello everyone, and I'd like to start by just going through the spectrum of standards that we have at Energistics. There are 3 of them, 3 main families, so they're shown there on the screen. So drilling is WITS-ML, production is PRODML, and reservoir engineering is RescueML. And these are families of standards built largely around XML schemas and XML documents, and they're underpinned by a couple of common standards. So there's the Energistics transfer protocol, which is how you transfer these documents, and then there's a common technical architecture, which is basically the standards which underlie the standards, so things like units of measure, and how these schemas are formed and so on. And so the idea is that these 3 sections of the upstream industry can share knowledge across them, so they're interoperable. So drilling, production, and reservoir data can be exchanged seamlessly depending on the context that's required. So that's the family of standards. Now, just going into PRODML itself a little. Oops, I've gone 1 slide forward, I think, there. Okay, can you help me on this, Phil? Just get me to the PRODML slide. So PRODML has several areas. The first of those is volumes, and so that's the most basic requirement for production data, if you like, is the volume of oil, water, gas produced or injected, whatever it is. Secondly, we have the fluid itself, so the PVT, lab analysis, sampling, and fluid characterization. So that's all about the fluid. And then we have the flow tests, so production tests, pressure transient tests, formation testing. Now, some of these may actually be done during the drilling phase in formation evaluation, and they'll probably impact on the reservoir phase, so the reservoir engineering. But because of that interoperability I just mentioned, they can be used where needed in the life cycle of the well or the field. Then we also have flow networks, which are really very relevant to production engineering, like the photo that we see there, what connects to what, so that we know where we're referring to when we talk about flows. So those are the kind of basic production data. And then we have these 2 families of distributed production data, so distributed temperature, DTS, and distributed acoustics, DAS. And so we're going to focus here on DAS in this presentation. If you can get us forward to the next slide, Phil. So the DAS measurement is really as represented on this slide here. So what it comprises hardware-wise is an interrogation unit. That's a box. We can just stay on the previous slide actually. And then we have attached to that a fiber, and that fiber will run across the surface to some length, might be along a pipeline or a flow line, and then it'll go down a well, or potentially even more than one well. And the way this works is that that fiber is divided by the interrogation unit into a series of loci, or each one being a locus, along the fiber, and that's a point at which we measure the acoustic energy. So you can see them there numbered across the surface and then down the well. And really what we're doing is we're measuring the sound intensity at these different points at a series of times. And so we're creating an array like the one shown there on the right, so that each column of that array is a moment in time and is like a snapshot of the acoustic intensity at those different points. So the rows in the array represent these loci, and then each column is a time instant. And so if you look at one locus there, you get a time series, which is basically the sound, like a microphone at that point. So next slide, please. So how does this work is by the pulsing of light. We've gone forward one too many there. The pulsing of light from the interrogation box down the fiber, and the backward reflection of light back up to the surface, and that's animated there in that little diagram on the right. So as the pulse goes down, light is reflected back, and that continues after the pulse has got to the bottom of the well. And so the detector is really measuring a time series, that the mapping, which I just mentioned, it basically chops that into these loci and records the energy at each point. And then this process shown in that animation repeats at, say, 10 kilohertz, and therefore you get the sound field at any one of those loci. And so the key point about this is that we need arrays, and we have very large volumes of them, because if we have several hundred loci and we're repeating the measurement at 10 kilohertz, then there's a lot of numbers that we're going to have to store. So that's the principle of it. If we go on to the next slide then, please, Phil. So the next slide shows just the conceptual model for these arrays, and the key point here shown on the left is that there's really two kinds of array. There's the raw measurement, which is what I've been describing, and then there's various kinds of process data, and we've dealt with two common kinds of process data in this standard. So FBE is the frequency band extracted energy, so that's the energy within a band of frequencies, rather than the raw, which is all frequencies. So this is like a reduced set of sound intensity, and each band of frequency will give its own time series at each locus. And then spectra is the power spectrum, so that's taking that raw data and mapping it into power spectra. So there we have spectra data. Now, all of these arrays have a time element in common, and the time is always stored in its own array, if you like, a one-dimensional array. So if you look there on the right, you can see that we have the array of numbers, but then, as I said earlier, the array has the locus as one index and then the time as another. So to find the actual real time that a column corresponds to, we'd look up in the time array, go to the appropriate number index of that column, and the value there will be the actual real time of that single measurement. So the first point is these arrays are very large, and we use HDF, so we're not using XML for these arrays. That would be too inefficient, so they're stored in HDF. So if we keep that in mind and carry on to the next slide, please, Phil. So that's the actual numbers of the measurement, but what we also need is metadata, And there's really several kinds of metadata, but clearly one important one is the stuff shown on this slide here, which is the hardware. So this just shows some of the main elements of the optical path, as we call it. So there's the instrument box itself, and then different sections of cable. They might be joined together by connectors or splices of one sort or another. There may be defects, known points where we know there's something not regular with the cable, with the fiber, and then it'll end at some point. And then also we should know how it's been conveyed into the, well, it might be on a fiber optic or coil tubing or wireline type logging approach, or it might be permanently in place, like it's cemented, for example, like it shows on that diagram. So we need to gather this information together. So if we go on to the next slide, please. So the metadata in this standard is stored in XML format. And the reason for that is we're familiar with XML and we can control it with schemas. And these are quite small files. So this is more like the traditional Energistics standard. Now on the right there's quite a lot of complexity, but what we're trying to get across is that we have to know where these loci are. The tap test there refers to calibration type data. And then we have to know the equipment, as I was mentioning earlier, the connectors and segments of cable and so on. And so we have, we've got a series of XML metadata files. So we have one for the instrument box there, shown in the green. We have another one for the fiber optical path, and that has things in like the inventory. There you can see in the little call out box is the actual material, the stuff, if you like, that's in the path. The network is the order it's connected up in. The facility mapping is, you know, is it along a pipeline? Is it down a well? You know, is it where there's a packer? So it's the kind of matching of these lengths into the real world objects. And then OTDR is a form of survey to assist with the calibration and diagnosis of that equipment before it's used for a DAS or DTS. So that's the hardware. And then the DAS acquisition object is another XML file, and that contains calibration information. So that's the detailed mapping of those loci that we were looking at. You know, where are they in space in terms of measured depth or distance along a pipeline and so on, and then all the parameters about how these arrays were generated. So the variables of the instrument box effectively that govern things like the sampling rate and so on, so that somebody can look at the data and understand how it was measured. So that's the metadata concept. So if we go on to the next slide, please. So yep, just go back up one. So this gives us rise to two types of data. If we can just go back up one, there we are. So we have XML files. Now they're shown there as red boxes. So they were the ones I've just been talking about. So they're all concerned with the metadata of the equipment and of the way it was used in the acquisition. At the bottom of the slide, we have HDF5 files, and that's with the arrays. So these are binary files, much more efficient at holding the numbers in arrays, but they're very large. And also there's no such thing as an HDF schema, and so we don't want to have to put too much metadata and structure into those, but it's very good for holding the numbers themselves, the arrays. And so between those, in the brown color there at the middle of that diagram, we have these proxy files, and they're very small files whose purpose is to navigate from the acquisition. So if the acquisition had a number of raw data measurements made, and then they were processed in different ways into spectra or FBE data arrays, there'll be, for each of the physical arrays, there's a proxy file, and that's what that is a small file that basically tells you where to find in the binary files, these big array files, where to find this array. And Kit's going to be explaining how all this works in a minute. But the point about that is you can open up these small files rather than having to go to these huge files that might be, you know, a whole hard drive just of data. And so it's much more efficient way of finding what you've got in the data set. And then finally, that grey coloured ellipse is an EPC container. That's the Energistics packaging convention, which is basically the same as Microsoft Office. XLSX, for example, file is a zip file with a very similar structure to this, and that's where that standard has come from. But it's basically a way of keeping together all these XML files in one container file that you can then open and look at them and discover these relationships which are shown. So that's a brief overview of how the system works as an acquisition, and how we've had to approach the data that's required. So I'm now going to hand over to Kit, who will go through the details of how this has been implemented and what to look out for. So if you can arrange for her to get control, Phil.
Yep.
She has control.
Thank you, Laurence, for giving this overview. That is really helpful. So in the following slides, I'm actually going to focus my attention on the HDF5 files, because the XML files are already very well described by the XSD schema, and it's also common, it's using a common architecture with the other MLs, so you're probably familiar with it. But the HDF5 files are the standard is more specific to DAS, and I would like to talk you through some of the details, and hopefully that will be helpful for you to adopt this standard. Okay. Oops. I think I pressed twice. Oh, okay. Yep. So this is just to illustrate example layout of how your XML and HDF5 files might sit together. So on the right-hand side, this is an example directory layout where you have one EPC, which is the zip that Laurence mentioned, that contains all of the metadata in XML format, as well as the file proxies. And the HDF files tend to be stored outside of the EPC because they tend to be very big. You don't want to zip many gigabytes of data together. Your file system might not want to handle that. So on the left-hand side is showing you a structure of how these objects are linked. So you have, for example, the DAS acquisition. And in this example, it has one FBE data, one spectra data, and one raw data. And they might be stored in separate files. In this example, the FBE, the different data type are stored separately, but within each data arrays, within each data set, it might be, the arrays might be too big. You still want to split it up into multiple files. One takeaway from here is that each HDF5 file should have one file proxy in the EPC, and you can have different layout to this. So this is just one example. So you may not have FBE data in your data package. You might have two raw data sets, and maybe you have it in a different decimation, one decimated more or the other decimated less, but they both refer to the same DAS acquisition. And you can likewise use the same layout and store these data arrays separately. Oops. Okay, or you can mix and match. You have two HDF5 files where one raw data set, you have half of it stored in one HDF file and the other half stored in the second HDF5 file, where the second data array share the same data files. So you can do mix and match depending on your business use case. And I also want to bring in the calibration into this picture. So Laurence mentioned the calibration allows you to map between loci to your facility length, basically position in your facility. And typically you might have thousands of loci, and it might not be practical to store all of these calibration points in XML. So it will be more practical to store them in HDF5. And so we extend the same logic of how we store raw or FBE data arrays for calibration. So in this example, your DAS acquisition may have two facility calibration, because you might have two facilities in your optical path, and they have separate calibration, and they can be sharing the same calibration HDF5 files, or they might not be. There's the same logic applies here. You can change the layout as you wish. So if you try, if you hope that you want to adopt this standard, and there are two directions which you may go about adopting it. So either you start from the EPC, the XML file first, or you start from the HDF file first. In my opinion, I think starting from the EPC is a better way to get familiar with how the data sets are linked and organized, because you will look into the specification in the XSD schema. You will look at how the data objects are related to each other. So it helps you to understand the standard and how things are linked to each other. But in practice, we notice that businesses tend to approach this adoption by implementing the HDF file first, because it allows quicker deployment of software, writing data arrays. You can quickly dump your data arrays into HDF files, write attributes as long as you understand what attributes are required. Then you can deploy these files to your customer. But this is a short-term quick solution. But then the cons is that it comes back to bite you later. As your data array grows, indexing many HDF files require you to read all of the attributes. And you also have to apply some assumptions on how the files are stored in your folder. So I have to assume certain directory structure. So it's not very scalable. It'll be much better if you have the EPC, which has all of the references and metadata that allows you to go from one file to all the other HDF files. So essentially the EPC serves as the index. So you don't have to scan many HDF files, you just have to read the one EPC. But because businesses find it useful to write HDF file first, it's not very practical if you just write arrays and not write any attributes. So consequently, some of the metadata essential for the DAS data arrays are repeated in HDF files to support most common business use cases. And then these attributes become part of the standard as well. So if you want to adopt PRODML DAS, you will have to comply with these standard of what kind of attributes you need to write in the HDF files. So I will will go into details of what you need to write. So here's an example of a HDF file duplicating some of the attributes in the EPC. On the left-hand side, it's showing you the content of an HDF file of a Word example for PRODML DAS. And the DAS acquisition is represented here as an HDF group. And some of the acquisition attributes is written here, for example, the gauge length or maximum frequency. You can find the same attributes here in the EPC. So on the right-hand side is in fact a collapsed screenshot of the DAS acquisition object in XML. So you can find correspondence between these two, that attributes in the DAS acquisition in the XML are repeated in HDF5. But the consequence of this is that if you have multiple HDF5 files, all these attributes are repeated in the same way. So in here, I'm showing you two HDF5 files that is in the same EPC data package. And I'm showing you that this acquisition group has the same attributes in both of these files. So in EPC, these values occur only once because they're stored in just one XML file for the same DAS acquisition object. But for your HDF files, these are repeated. So the implication of this is that these attributes are repeated more than once. So if you want to edit them, you have to edit it in multiple places. So this is a drawback here, is that you may risk having these attribute values being unsynchronized. Okay, so you may want to ask, what are the required attributes then? So on the left-hand side, again, I'm showing you an example, HDF files. And then in the middle, I am showing you the UML of the DAS acquisition XSD objects, which actually tells you what attributes are defined in this DAS acquisition and how whether they are required or not. For example, acquisition ID is required because you don't see this square bracket 0 to 1 or 1, etc. In XSD, it will say, so it is actually is required, its minimum occurrence is 1, maximum occurrence is 1 as well. And likewise, spatial sampling interval is also required. But then the ones that are grayed out here are optional. This is, so okay, the flip side is that the ones that are not grayed out are required. And there are 2 rules in here. First of all, if the attribute is the basic type, or if it's a measure type, and if it's required in XSD, then it's required in XDF5. And measure types, examples of these measure types are length measure, frequency measure, which we can find in here is minimum frequency is a frequency measure. And if it's a measure type, then units is also required. So you need to write the units as x.uom. So in the left-hand side, you can see example, such as minimum frequency dot UOM equals hertz. So the minimum frequency is in hertz. One thing you also want to pay attention to is that DAS acquisition in this example is extending from the abstract object. So it's inheriting abstract object, which itself also contains 2 required attributes. One is schema version, another one is UUID. This may all sound very complicated, unfortunately, but I would like to refer you to the documentation, the PRODML DAS Technical Usage Guide, chapter 24.6.5. And I try my best to make sure that this slide and the documentations are consistent, but if you find any mistakes here, please refer to the documentation. Okay, so here's another perhaps gotcha when you write HDF file or EPC, is that there are 2 UUID looking attributes for DAS acquisition. One is called UUID, another one is called acquisition ID. So UUID, or I can show you here on the right-hand side in XML, is the unique identifier for this DAS data package. And but the acquisition ID here is referring to your DAS acquisition job. So when you might have different values, well, you might have one DAS acquisition job and you create a data set containing only raw data for this acquisition. So you have a EPC created for that, and you have one UUID. And for the same acquisition job, you may post-process your raw data and create another data set containing only FBE data. So you have another EPC. So these 2 EPC will have 2 different UUID, but they will have the same acquisition ID because they are referring to the same DAS acquisition job. So that's how you may link data sets together. They are both describing the same acquisition. Okay. So next thing I want to mention is that the HDF5 data structure imitates the structure in XML. So on the left-hand side, you can see the content of an example HDF5 file where it contains raw data, FBE data, and spectra data. And on the left-hand side, on the right-hand side is a UML of the data object defined in PRODML DAS, and you can see the correspondence between the 2. And I would also like to refer you to the documentation again, chapter 24.6.4, which actually tells you what HDF group path you should be writing for each of these data group and data sets. Okay, so next things I want to mention is that HDF5 file has a UUID to identify itself. If you are tackling this adoption from using the HDF5 only approach, then you might not have an EPC, then this UUID is not used because in fact this UUID is used for referencing from the EPC to HDF5. So in here I'm showing you a relationship file in the EPC which contains a UUID referring to HDF file. It also contains the relative path of the file, of the HDF5 file relative to the EPC. And so in this case, if you don't have EPC, you realize, okay, this UUID is not used, why am I writing it? But it's a required attribute. So if in the future you want to retrospectively create an EPC, you will need this UUID. And the other thing I'd like to mention here is that because we need to refer to HDF file from an EPC using this relationship file, and the relationship file necessarily needs to contain the relative file path, it means that you can, once you have an EPC together with your with the HDF file, you cannot rename your HDF file. You cannot rename your HDF file without modifying your EPC. Otherwise, the link is kind of broken. Okay, so the other questions you might also have is, okay, if I have a big data array and I store it in multiple HDF files, how do these file paths get linked? Let's say you want to try to read it, how do you link multiple files together? And this is an example showing when a raw data array is split into 2 files, you can link them using the UUID of the DAS raw object. So on the left-hand side, showing you the content of 2 HDF files, and in the raw HDF5 group, you can find the same UUID being written in both of these files. And in fact, it's the value of this UUID is also found in the EPC, and it will occur only once there. So note that this UUID is not the same as the UUID of the DAS acquisition. This is a UUID for the raw data group. So that might sometimes confuse people. Okay, there's so many UUID, or maybe they're all the same. They're not the same. Okay, so it's actually the same example files here. Okay, now I can link 2 file paths. How do I order them? I have one data array split in half. Which come first? These data parts are split along the time axis, and you can use the start index attribute to order them. So for example, in part 1H5 on the left-hand side, the raw data has a start index 0. And so that data array comes first in the time axis. And then in part 2H5, the start index is 37, which means it's actually the 38th timestamp in this data set. So this is the second part of your data array. And again, you can find all these metadata in the EPC. So if you have an EPC, you don't have to scan all of the HDF5 files, you just look at the XML. You can find that, for example, on the right-hand side, the raw data have got 2 file proxy. And you can see immediately that one file proxy's got start index 0, the other file proxy's got start index 37. It even contains the HDF path for you to go directly to find your data array. So that's the path in external file. You go to /acquisition/raw square bracket 0/raw data. You can go directly into the data array. Okay, so one more rules relating to writing HDF5 groups, and many rules, is that you should only write a HDF5 group if there is a leaf dataset you need to store. And then I'm here showing you an example for the calibration data objects, because we haven't shown it very much. And in this example, there are 2 calibration, and we have an HDF5 files because we have a mapping from all of the locus to the optical path distance and the facility lengths. And this is called the locus depth point, which is a full mapping for all of your loci. But this is an optional array because sometimes you may not be able to calculate the full mapping, or maybe because you just don't want to calculate it. And it might be a post-process. It might need to be post-processed later, and you don't want to write it straight away at the start. And if this is not included because it's optional, then you should not be writing any of the HDF groups. But okay, so that means if you can't find the calibration objects in HDF5 file, it doesn't mean there's no calibration. It could just mean that there is no complete mapping from the loci to the optical path distance. I don't know if that makes sense, but it is to illustrate how you may not have some of the HDFI groups which you might expect. So that brings us to questions. Okay, it looks like that HDF5 file seems enough. Why do we need EPC? And the calibration example actually illustrates that yes, you do need EPC because a lot of the metadata cannot be written in the HDF5 files. For example, if you don't have the loci, the full mapping from loci to from loci to optical file path, then it will not make sense to just store all of the content from XML in the HDF file. So it will make more sense to just refer to them in XML. And there are a lot of metadata that Laurence mentioned, for example, the instrument box, how the optical path is configured. All this metadata cannot be represented in HDF5 files. Also, a lot of the slides that I presented are related to how you should be writing HDF5 files. These rules are documented in words, so they are not in code, as opposed to how the XSD schemas are written. So misinterpretations are still possible. And if the writer and the reader have different interpretations on how the HDF file should be written, then it could it could cause incompatibility. If the writers are written by one company and the readers are written by another company. And HDF5 files cannot be validated without a custom-made tool because it doesn't have a schema like the XML files do. Whereas XML files, you can validate it using XSD schema very easily. So this is perhaps an ideal if all of the writers supply EPC. Then readers can find all the reference data arrays from the EPC. You don't have to scan off the HDF files. You can find your data directly from the XML. And in that case, then actually you don't need to write so many attributes in the HDF5 file. So that's kind of the ideal maybe for the future. Then all you need to read is just the file UID. So that's less work for the readers. And it will also be less work for the writers because, well, the writers now only have to write the attribute value once in the EPC. You don't have to repeat the attribute values and keep them in sync in the HDF5 files. So all you need to write is the file UID. So if in the future everyone writes EPC, everyone reads EPC, then it will be a lot easier to write the HDF5 files. So conclusion. The experience from these businesses who have adopted PRODML version 2.0 is that it's a bit involved, but it's perfectly workable once you understand the standard. And the version 2.1 is coming up. It's built on top of version 2 experience. So we have extended the documentation targeting the more common HDF5 first approach. We clarify some of the rules on what attributes need to be written, what data objects should be written, and data path, so on and so forth. The calibration data is also reorganized, and we also fix a number of bugs in the schema. And the version v.1 is now available for review and is intended to be released soon. And hopefully we will get more adopters for this target version. And I think I will hand this back to Philip.
Yes, thank you very much, Kit. I don't know how you do it, but you actually made such a subject very lively and entertaining. I'm impressed. And I certainly hope the other people following this event likewise. Now we're opening the question and answer tool, which you'll find at the top of your webinar screen or at the bottom, depending on where you located it. So please submit written questions, and Jana will be the one distributing the allocation of answering and all that. Jana, do we have any?
Nope, no questions so far.
Oh, Phil, if I could just add a comment.
Please.
Jay Hollingsworth. What Kit presented about the way you can create lots of multiple HDF5 files is pretty interesting. And the use case for that is even more interesting. I'm looking at the people who are attending, and some of the folks who are attending might not be aware why we would actually need to take a raw data set and break it up into multiple HDF5 files. And the answer to that is that this is a file transfer format, and mankind doesn't make disks big enough to be able to move an entire raw data set. I mean, the biggest enterprise scale disks you can buy is a 14 terabyte disk. So we have this situation where we have to break up DAS acquisition data sets, especially the raw data, into multiple files because we literally can't put it on a disk and move one disk. So a traditional job from an operator getting data from a service company is they'll get a box full of disks. And that's the reason for the use case that Kit was presenting, that you create a proxy for each of those, the files on each of those disks.
Thanks, Jay. That's certainly a very good clarification.
Okay, well, we we don't have any questions. Certainly, if anybody thinks of any, they're welcome to send them to us at, let's do standards@energistics.org.
Jana,
okay.
yeah, Jana, could I just suggest? Yeah, I was just going to say, I mean, it's probably worth pointing out that we've got a working group, and Energistics members are welcome to join that group. The development work is largely done, and so the group's sitting now more for the adoption support, you know, rather than to develop the standard. Now we've got this version 2.1. And we have companies who've given a contribution in kind, you know, in expertise or development effort, who are not members in the past. We've also allowed them to join on the basis that rather than paying up for Energistics, you know, a small company specializing in DAS, some of them have just joined, you know, and contributed in kind effort. So, you know, that could be something of interest to people on the call. And they should contact you, I guess, Jana, in the first instance.
Yep,
for that.
That would be fine. Or send that to standards@energistics.org as well. So either way is good. And 2.1 is out for public review right now. There's been some clarifications to the DAS documentation and some additions around calibration. So it's out for public review. And later this year, it'll be published as the commercial version, or at least commercially implementable version. Nope.
Right. So
No
I think
questions?
that wraps up. No. Okay, so I think that wraps up the webinar for today. Thanks again to the presenters, Kit and Laurence, for your hard work putting this together and presenting it. And as mentioned earlier, this will be available as a recording on our website to be shared. And there's a little Q&A survey that will come to you the moment this webinar shuts down. So thanks again, everyone, for attending. Merci beaucoup. And we'll be on the air probably a month from now with our next webinar. Look out for that on our event page.
All right.
Thank
Thanks,
you.
everybody.
Thank you.